Welcome to Calculus 1. In this lecture, I will be giving a basic overview of basic mathematical concepts. I want to preface this video by saying that this is not meant as an introduction to these concepts. Rather, this video is only meant as a refresher. Let us begin by discussing absolute values. The absolute value of x is defined as the following. If x is greater than or equal to 0, then the absolute value of x is simply x. If x is less than 0, then the absolute value of x is negative x. For example, suppose that x is equal to 5. Then what is the absolute value of 5? Well, 5 is greater than or equal to 0. So the absolute value of x is simply x. So the absolute value of 5 is 5. Now suppose that x is equal to negative 3. What is the absolute value of negative 3? Well, negative 3 is less than 0. So the absolute value of x is negative x. So the absolute value of negative 3 is negative 3, which simply gives us 3. Now let's consider an interpretation of absolute values. So what about the absolute value of negative 3 minus 2? Well, negative 3 minus 2 is negative 5. So we're really asking about the absolute value of negative 5, which is simply 5. But how can we interpret this number? Well, consider the following. The absolute value of x minus c is x minus c if x minus c is greater than or equal to 0, or it's negative x minus c if x minus c is less than 0. So here, in the absolute value of negative 3 minus 2, x is negative 3 and c is 2. If we plot it on a number line, we will see that x is at negative 3 and c is at 2. Here, the distance between negative 3 and 2 is 5 units. So we can interpret the absolute value of negative 3 minus 2 as the distance on a number line between negative 3 and 2. So rather, we can interpret the absolute value of x minus c as the distance between x and c on the real number line. Now let's talk about sets and intervals. We define sets of real numbers like the following. S is equal to x in the real numbers such that, and we place a condition on x. X in the real numbers is telling us where we are taking the numbers from, and the condition on x tells us which numbers we are keeping in the set and which ones we are throwing out. For example, consider this set. This set, we are taking the numbers from the real numbers, and we are placing the condition that if a number is going to be in the set, then when you square the number, it must be less than or equal to 2. So this is read S, x in the real numbers, such that x squared is less than or equal to 2. This set contains all values from negative root 2 to 2 inclusive. When defining sets containing real numbers, we can use something called interval notation. It looks something like this. We say x is in the closed interval negative root 2 to root 2. The square brackets denote that it's a closed interval, which means that both the lower bound, negative root 2, and the upper bound, root 2, are included within the set. If you were to plot this on a number line, it would look something like this. At negative root 2, we have a filled-in circle indicating that it is included in the set. At root 2, we also have a colored-in circle which indicates that it is also included in the set. Now let's talk about the different types of intervals we can have. So let a and b be in the real numbers, and we can have the following intervals. We can have the closed interval a to b, and it looks like this on the number line, where we have a colored-in circle at a and a colored-in circle at b. We can have the open interval a to b, where a and b are not in the interval. This looks like this on the number line, where we have an empty circle at a and an empty circle at b. We can have different variants, so a closed interval at a and an open interval at b, which looks like this, or we can have this, and so on and so forth. We can also have intervals going to infinity. Now, remember from the last lecture that infinity is not a number, so we always leave an open interval at infinity, which denotes that the set is not bounded from above or not bounded from below. Now let's talk about functions. Suppose we are given two sets of real numbers, an x set and a y set. A function is any rule that assigns each x value a single y value. For example, this is a function. We have a table where x is in one column and y is in the other column, and we explicitly assign the x value of -15, the y value of 1. So this is a perfectly good function. This might be something you're more familiar with, which is a graph. This is also a perfectly good function because it shows you the relationship between the x set and the y set. This is also a function that you might be familiar with, which is an equation. We have y, which is assigned to the x value such that when you put x into that equation, it will spit out a y value. This is also a perfectly good function. And finally, this is also a perfectly good function. The function doubles any number you give it. You can describe a function with words as long as it is a rule that assigns to each x value a singular y value. We can also have things called composite functions. So let's say you're given two functions, f of x and g of x. And let's say f of x is equal to x squared plus 2 and g of x is equal to sine x. The composite function, which just places g of x inside of f of x, is given like this. F of g of x, which is written like this, is equal to sine of x squared plus 2. And g of f of x is equal to sine of x squared plus 2. Now note that f of g of x is typically not equal to g of f of x. Let's now define what it means to say that a function is increasing. A function is increasing on an interval I if f of x1 is less than f of x2 for all x in that interval I. For example, suppose that we're given a function f of x is equal to x squared plus 3 on the interval 0 to infinity, and 0 is less than x1 is less than x2. Let's prove that f of x is increasing on the interval I. So let's start with what we were given. We are given that 0 is less than x1 is less than x2. We can multiply by x1 throughout the inequality, which gives us this. Now x1 times 0 is 0, and x1 times x1 is x1 squared, so we can write it as this. We can also multiply the inequality by x2. So x2 times 0 is 0, x2 times x2 is x2 squared, so we're given this. Now note the transitivity property. We have x1 squared is less than x1 times x2, and we have x2 squared is greater than x1 times x2. So this gives us the following inequality. x1 squared is less than x2 squared. Adding 3 to both sides of the inequality gives x1 squared plus 3 is less than x2 squared plus 3. This proves that for all x in the interval, x1 squared plus 3 will always be less than x2 squared plus 3. This means that the function is increasing by our definition. If you didn't fully understand this, that's okay. Try this exercise. Try to define a function that is decreasing. That is, what is the definition of a decreasing function? Further, try to prove that the function f of x is equal to x squared plus 3 is decreasing on the interval negative infinity to 0. If you can do that, then you would have understood this concept. Let's now move on to trigonometric functions. Consider the unit circle here with a right-angled triangle inscribed within the first quadrant. The length of the side of the triangle opposite the angle x is equal to sine of x. And the base of the triangle, that is the side of the triangle adjacent to the angle x, is equal to cosine of x. Further, the ratio of sine of x to cosine of x is equal to tangent of x. That is the ratio of the length of the side opposite the angle x and the length of the side adjacent to angle x is tangent of x. Finally, let's talk about some basic trigonometry. the arc length of the circle, that is the red arrow, is equal to the angle x times the radius of the circle r. When the angle x does a full rotation, that is 2 pi, the arc length is 2 pi r. This is the familiar formula for the circumference of the circle.